Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today we are going to talk about how to analyze the graphs of polynomial equations. We've done it. We've reached the point where we now know how to solve polynomial equations. We can multiply, add, divide. But we want to go back to the basics, back to the very beginning of this unit, back in 4.1 when we first started talking about how we know what a graph looks like. Today, our goal is going to be to talk a little bit more about the specific parts of a graph. Now, there's a lot of vocabulary, and I want to start off by talking about something called the location principle. The location principle is a really interesting concept, but it's also pretty self-explanatory. Let's say I had a building, right? I'm actually going to draw this in my example sideways so we can all see it like a skyscraper. Let's say I'll draw it this way. It'll make sense later. Let's say I've got a building, the Mr. Strager skyscraper. And the Mr. Strager skyscraper has a lot of floors. It has 10 floors. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. At 0 is where the ground is, but I also have 3 basements. I know it's a very fancy tower. If I was starting on the top floor and I wanted to get to the bottom, no matter what route I take, I am guaranteed to pass under the ground. I am guaranteed to go through the ground floor. Sure, maybe I go straight down on an elevator. I still pass through 0. Maybe I take a really curvy, sharp way back down. I still go through floor 0 no matter what. The location principle says that no matter what, if f is a polynomial function, if f is a polynomial and a and b are points where f of a is less than 0, that's like being underground, and f of b is greater than 0, it's like being above ground, then f has a 0 between a and b. Then there is a 0 between A and B. Really weird way of explaining it, but the basic concept is this. On any graph of a polynomial ever, if you are trying to pass from a point that's positive to a point that's negative, you're guaranteed to pass through one of the zeros of your polynomial. So here's a polynomial I have right here on my graphing calculator. Let's say I had 2 points on it. Let's say I was looking at a point right here. Actually, let me click trace just so we can be a little more exact. Let's say I had a point right here, right above 0. And I have a point here below 0. I am guaranteed to have a 0 somewhere in between them. What that 0 is, don't know. But because we go from positive to negative, or negative to positive, there's 0 in between. Next up, we're going to start actually describing graphs. So here's what I'd like you to do. I'd like you to take out your graphing calculator. We're going to need it for today. And I'd like you to graph the following function. I want you to graph y1 equals 3x to the 4th minus 6x cubed minus 3x squared plus 6x. Pause the video here if you need a second to type it out. Before I click the graph button, what do we know about this graph? What do we know it's going to look like? Well, let's jot down a couple of things up here. First off, the degree is 4. What does a degree of 4 tell you? Do you remember from Unit 1? If your degree is even, we know that it's going to give us a lumpy parabola. Our degree is 4, so we know this is going to be a lumpy parabola. All right? What else do we know? Well, our LC, our leading coefficient, is 3. Since our leading coefficient is 3, that tells us that our lumpy parabola is going to be facing up. When I graph this, it should look something like this. Now, if I wanted to be even more precise, which I totally could be, I could factor this out into its component parts, see what I get, and graph the zeros. I'd be even more exact then. I have a much better way of determining what the graph looks like. In fact, let's do that real quickly. So, I want you to take a minute and try seeing if you can factor this. I'll give you a hint. Grouping absolutely will work with this. You may absolutely group this function. Pause the video, see if you can find the zeros, and we're going to see if we can make a more accurate graph. How'd you do on the factoring? Hopefully we should have gotten something that looks like this. Now remember, if we want to find the zeros of this, we can set each piece equal to 0 and figure out what x should be. So it looks like here, x equals 0, so we know there's going to be a point where it touches or crosses here. And since we don't have a repeated root of 0, we know it's going to pass through 0. It's not just going to touch and bounce off. Let's keep going. Here, we have an x of 1. Here we have an x of -1. So we know we're going to get 2 points there and there. And we know we have an x of 2. So we know we're going to get a point that crosses through here. It looks like our lumpy parabola is pretty much good. We know that it's going to be a lumpy parabola. So it's going to start at the top, it's going to end at the top. And it's going to pass through all of these points since they're not repeated roots. So our lumpy parabola surely must look something like this. Maybe it goes up here, and down here, and up here again. Right? Or, wait a second. Maybe it looks like this. Maybe it's like super, super long. Like bam, 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 and bam. No, wait. Maybe it's super, super shallow. So much so that we don't even really see it going up and down. We don't know what this graph actually looks like. We have a good idea, but we don't know exactly what it is. This is where we start to analyze the graph using maximums, minimums, turning points. A local maximum is a hill, basically. It is the highest point in a region of nearby points. So we'll say the highest point of all nearby points. If we look at the red graph, we see that there's no total maximum. There's no highest the graph ever goes. It goes on forever. But we do see we have a local maximum. We have a spot where it's higher than the points around it. This is a local max. Think of it like the top of a hill. The highest point of all nearby points. The top of a hill. And I'm going to even draw like a little point or a little hill. Right there would be a local maximum. The local minimum is the lowest point of all nearby points. Of all nearby points. So we can say the bottom of a valley. So maybe we have a valley here. It's going to be the very bottom. On our graph, we can point out some local minimums as well. There's 2 spots where it goes really low. Here and here. You can also kind of think of these as like vertices. Like remember on parabolas we had to find the vertex? Local maximums and local minimums are like vertices, or vertices I should say, of a polynomial. There is one last thing to mention. Both of these, local maximums and local minimums, are also called turning points. These are called turning points. And it's where the graph changes direction. So the turning point is where the graph changes direction. Both local max and local minimums are turning points. Anytime we see our graph change from going up to going down, or from going down to going up, we call it a turning point. And if we knew where those turning points were, we would have a much better time of graphing. We'll get back into this a little bit later, but unfortunately we're not going to learn many methods for finding these turning points. In pre-calc and calculus, oh, it'll be everything. But for this, not so much. These two words look familiar. Domain and range. We've definitely done domain and range before in Algebra 1, but it was probably a little bit tricky. So here's what I'd like us to do. I'd actually like you to turn these two definitions into one big graph with 3 notches on each axis. 1, 2, 3. 1, 2, 3. And I'm going to make a weird looking parabola that starts and stops in different spots. So I'm going to say that this parabola, not parabola, I'll say we'll make it a polynomial, has a point here. I'll say it has a point down here. I'll say it goes back up in this direction and goes up forever. I'll say it has a point down here and then goes up forever in this direction. Weird shape. It's going to be a very lumpy parabola here that I'm making. Boop. It goes down there, it connects there, it connects there, and it goes up through this point here. Perfect. We want to somehow characterize how big this parabola is. So there are 2 ways we can talk about it. We can talk about how far to the left and right it goes, and how far up and down it goes. So let me label these points to make it a little easier for you. I'm going to label this turning point as -2, -1. This will be -1, 2, and this will be 1, -2. For the domain is just a list. It's a fancy way of saying a list of all possible x values from lowest to highest. In other words, left to right. Here's something interesting. Do we ever stop going to the left and going to the right? I mean, the graph seems to go up a while, but you see how it keeps going on to the left. This one might be at x equals -3. In fact, this point is at -3, 1. But it goes even further than that. It goes to -3.5. And it's probably going to go to -4 if we go on, and -5 and -6. Is there a most to the left we go? No. We never stop going to the left. So there's no lowest point here. What about the highest point, or the most to the right we go? Well, sure, we pass through this point here. This point is at 2, 3. But notice how it keeps on going. This arrow is also going to keep going to the right forever and ever and ever. If your graph goes to the left forever and the right forever, we say the domain is all real numbers. All real numbers. If it ever stops, sure, you can say where it stops and starts up again. Maybe our graph, the lowest it ever goes is -3 and the highest ever goes is 2. But our graph has arrows, it goes on forever. Another way of writing all real numbers, we talked about this actually before, is using the symbol for the number system for the real numbers. Remember this funky R? That's the symbol for all real numbers. Similarly, the range is a list of all possible y values, lowest to highest. So here we're looking for the most far down and the highest up. Our graph goes up forever. Cool, it's going to continue on until infinity. But do we have a lowest point? We actually do. This dot here is lower than this dot here. This is our lowest y value. And it's a y value of -2. To write out your range, you want to write it as an inequality. Since we're talking about range, we're saying our y values are here. If we know the lowest value, it goes on the left. If we know the highest value, it goes on the right. If it goes on forever in any of those directions, we don't write it. So since we don't know a highest value, we keep the right side blank. But we do know a lowest value, -2. And since -2 is lower than all the other y values, we say -2 is less than or equal to y. That's our range. We'll do some more examples of this a little later, but it takes practice. We'll talk about even and odd functions in a little bit as well, but I hate how these are named. I hate they're called even and odd because they really don't have anything to do with even or odd numbers. Let's flip the page and talk about turning points. A turning point is where a graph changes direction. You can think of them like vertices. However, there are two rules about turning points. The most amount of turning points a graph can have is one less than its degree. So if we have a degree 4, for instance, equation, hint, hint, and we graph it, the most amount of time it's going to change direction is 3. And if we graph this one, we see that's exactly the case. 1, 2, 3. If a polynomial has n unique zeros, meaning that there's no repeating roots, it has exactly that many turning points. Let's compare something real quick. Let's say I had a repeated root x minus 2 squared times x minus 1. This is going to give us a different graph, a red graph. And when we look at this, we look at the degree that this would give. This will be x squared times x. It's a cubic. This says the most amount of turning points we're going to have is going to be 3. Sorry, it's a cubic, so it's going to be 2 at most. However, if we look at our graph, it only has one turning point, right there in the middle. You can have at most n minus 1 turning points. It is not necessarily exactly n minus 1. Only if there are no repeated roots will there be exactly that many turning points. Again, we will find a much quicker way of finding these turning points in pre-calc, but we're going to find them graphically here. So let's do an example. Let's graph this equation on our calculator. The first question is going to be, how many turning points are there? Before we answer that question, I want to ask you, how many turning points are possible? Well, since this is degree 3, we know that there are going to be n minus 1 possible turning points. Since it's degree 3, that means there are going to be at most 2. There could only be 1. But if we look at the graph, we see that there are 2. That means all our zeros are unique. We have different zeros. In fact, there's only really one zero here. All right, we want to sketch the graph and label these turning points. But how on earth can we graph this from here onto the paper? We want to be exact. To be exact, use your table. Whoops. I think my table is being a little bit bizarre. I apologize. If your table looks like this, just look down at the bottom to see what the values themselves are. So for instance, 0 and 5 work. Down here, 1 and 3. Down here, 2 and 19. So graph it this way and come back in just a moment. Here we have a couple of points. We can use these to generally graph what our graph will look like. Let's find some of these turning points. Remember that the turning points are local maximums and local minimums. So do we see any? Yeah, we've got two of them. We've got a local max right here and a local minimum right here. An L max and an L min. To find out what these values are in Algebra 2, the way we do it is we want to calculate these maximums and minimums. So go to second and calc, and we can actually figure out what the minimums and maximums exact values are. So if I go to minimum, it's asking for a left bound, and it'll ask for a right bound. Therefore, we want to find a place to the left of our minimum and a place to the right. So I'm going to choose right here. If I zoom in a little bit so you can see exactly what we're talking about, let me zoom into the minimum, just so we can see. I want a place to the left of that minimum. I'll go right here. A little dotted line appears to show that this is the place. We want a right bound, so let's go to the right of the local minimum. Once your local minimum is between these two lines, you click enter, and it'll zoom right into the spot. We don't have exact numbers here, and that's okay. We are going to estimate these points, approximating them to a reasonable degree. I'm going to go with 3 decimal places. So this is point 0.745, comma 2.515. Done. This is our local minimum. The local maximum, the place where it reaches its highest peak, we will find the same way. So let me go back to my standard zoom. Whoops, clicked on the wrong one. Let me go to my standard zoom, just so we can see the graph again. And let's find the local maximum. We go second, calc, and we find the maximum. We go to the left, we go to the right, we click enter, and there's our local maximum. Interestingly enough, it's negative 0.745, whereas this one was 745. And it has a y value of 7.485, basically. Interesting. The last thing we want to do is find the domain and the range. To find your domain and your range, we are looking for the most to the left our graph will ever go in its life, and the most to the right it will ever go, the furthest down and the furthest up. It seems like 2 is the most to the left it goes, but we see that this arrow continues on a little bit past it. It goes even more to the left. Likewise, we're going to continue going to the right this way here. Our table doesn't just suddenly stop after 6 or something. It goes on forever. If x can be anything towards the right and anything towards the left, what do we use for our domain? Our domain is all real numbers. Let's look at all of our y values. Does our y value have a lowest or a highest point? Let's find out. I'm going as far down as I can, It's going pretty far. This does not have a lowest value. The arrow goes down forever. And even if I go into the positives, even if I try to see what the highest point we ever go to is, it never stops going up. That means our range is also all real numbers. Your range is all real numbers if you never stop going down or never stop going up. Next up, we are going to talk about even and odd functions. Right out the gate, these have nothing to do with even and odd numbers. If you see a 2 somewhere, it's not immediately an even function. If you see a 17 somewhere, it's not immediately an odd function. Even and odd functions talk about the symmetry of a graph. Let me give you an example here. Is this graph symmetrical? Not immediately. I mean, it looks like if we were to cross it down this middle line, it would not look the same on both sides. There's some different kinds of symmetries that we are going to look out for. Symmetry is not just something we can see in a picture. Symmetry is also something we can see in an equation. Think back to Unit 1 when we were doing all of our transformations. In fact, think about 4.7 when we were doing all of our transformations. And we were flipping things over the axes. That's one way something is symmetrical. Let's take a look at this graph down here. It's a lumpy parabola. Notice how we have some symmetric points. On the left, we have negative x comma y. On the right, we have positive x comma y. Let's pretend for a second that up here we have the point, I don't know, negative 4, 3. On the other side, we would have positive 4, 3. This graph is symmetrical in the sense that if we cut it straight down the y-axis, it looks the same on the left as on the right. In other words, whenever we have a negative x, we also have the same positive x. Negative 4, 3 is the same as 4, 3. This is what an even function is. An even function is when for every single point, and it needs to work for every point, you can flip it over the y-axis and get the same y value, just with a negative x value. So if I told you that this point down here was negative 1, negative 2, for this to be symmetrical, this point here, where it's another turning point, would have to have the same y value, negative 2, but the positive version of the x value, 1. Pretty simple so far. And then odd functions come in. Odd functions are super, super weird. For an odd function, all of your points should be reflected over both the x and y-axis at the same time. What on earth does that mean? Let me give you an example. Let's say I gave you the following point up here. Just a random spot. Well, it's in the negative x's and the positive y's, so we'll call it negative 5, 3. A function is odd if mirrored across the y-axis and down over the x-axis, there's an identical point, but both our x and y values have their signs flipped. So this would be positive 5, negative 3, for instance. Everything has to flip. Super, super weird. Before we go any further, I want to discuss what the implications of this are. If you have a graph that's even or odd, just knowing one side of the graph makes it so you know every other point on the other side. But let's figure out if you can determine something is even or odd from an equation. Now this is funky. This is weird. we have to use a couple of very quick guidelines. The guidelines I have for you are this. We're trying to see what happens when we flip our x values. We're trying to see what happens when we have a negative version of our normal x value. That's how we can tell if something is even or odd. So if f of x equals x cubed minus 7x, let's figure out what f of negative x will be. Here is the key. If we end up with the same thing, if we end up with x cubed minus 7x, it means positive x and negative x give you the same outputs. It means this is an even function. If we end up where we have a negative x cubed and a positive 7x, it means that we have an odd function. If neither happens, it's neither even nor odd. So let's replace all of our x's with negative x. So here, for instance, I would have negative x cubed minus 7 times negative x. What happens if we replace them with negatives? Well, negative x cubed, that's negative x times negative x times negative x. A negative times a negative times a negative is a positive. Or sorry, it's another negative. 2 negatives make a positive. 3 negatives make it still negative. So this is negative x cubed. And negative 7 times negative x is positive 7x. What have we just done? We figured out it's not even because they're not the exact same. Let's figure out if it's odd. To figure out if it's odd, let's pull out the negative sign and see what happens. If we pull the negative sign out from both of these terms and put it in front of parentheses, we would end up with regular x cubed and negative 7x. What does this mean? It means it's the same thing, just negative. And if it's the same thing, just negative, it's an odd function. An odd function happens when, if we change our inputs to be negative, the output is also changed to be negative. If we change our inputs to be negative, our outputs will also change to be negative. It'll be negative of whatever we started with. That's an odd function. Let's see the next one. On the next one, let's do the same thing. We have f of x. Let's see what happens when we plug in negative x here. So if we plug in a negative x, that'd be negative x to the fourth plus negative x squared minus 1. We have changed all of our inputs to be negative. We've flipped over the y-axis in a sense. Well, negative x to the fourth, that's a negative times a negative times a negative times a negative. 2 negatives make a positive, so it's a positive. 2 negatives make a positive, that's another positive. It's just going to be positive x to the fourth, isn't it? Plus, negative x squared is just negative x times negative x. That's also going to be positive x squared, and that's minus 1. Hang on a second. Here, we ended up with the same equation, even when we changed our inputs to be negative. Something is an even function if, when you change the inputs to be negative, you end up right where you started. It's the same dang thing. Last but not least, let's try this one. F of x equals x cubed plus 2. We're just going to make our x into negative x. So that would be negative x cubed plus 2. Negative x cubed, isn't that just negative x times negative x times negative x? That's just going to be negative x cubed. plus 2. Okay, it doesn't look the exact same. So we should do our next step. We should see what happens when we pull out a negative from both of them. We know it's not even because they don't look the exact same. But maybe it's odd. If we pull out the negative, let's see what we end up with. We end up with x cubed minus 2. But that doesn't look the same either. Here it was x cubed plus 2. Here it's x cubed minus 2. This means that this graph is not symmetrical even when you flip it twice. It's not an even because it's not the same. It's not an odd because it's not just a negative. It's neither. And we're done. Thank you so much, everybody. That concludes our notes for today. I hope you have a fantastic rest of your day.